Okay, so when I drew this figure, I said, okay, given the angles theta 1, theta 2, theta 3, compute x, c, y, right? That is the forward kinematics problem. Okay, here we are not doing this. Here, x, c, y should be x reference, y reference. This part is given. So we know where we want the end effector to be. What is unknown is theta 1, theta 2, are unknowns. So let me write it on words. Given reference position for the end effector, compute the joint angles. Okay, so what we'll do is, turns out that we'll do a very specific problem today, and then I'll show you that you can actually solve for this manipulator. You can do it analytically, which is nice. But most of the time you cannot do this analytically, and we'll resort to a numerical package. So let me pose the problem. Here you can see the way I've specified it. There are two things defined, xref, yref, and there are three unknowns. It actually is a nice thing to have. You have an extra degree of freedom. I'll actually constrain this to three things given. That way, it's sort of there's only few solutions and not infinitely many solutions. So if you have this kind of problem where two things are given and you're asked to find three numbers and it's infinitely many solutions. So I'll constrain it a little bit. So here is the problem. Given xref, yref, theta ref, this will be the orientation of the end effector. Compute theta 1, theta 2, theta 3. Okay, so let me draw the manipulator. In some positions, such that thetas are all positive, it makes it easier to do the calculations. Okay, we assume these lengths to be L1, L2, L3. Okay, so what's given is we are told that the end effector needs to be at xref, yref, and then we also told that the orientation of the end effector, the absolute orientation, should be theta ref. Now it's easy to see that this angle, the last angle I showed, is actually theta 1 plus theta 2 plus theta 3. Right? Because what is this? This is theta 1. And then what is this? This is theta 1 plus theta 2. Okay, so we will solve this using an algebraic method. Okay, we need to specify, given L1, L2, L3, can we figure out the position of the end effector, that is X, C, Y, E? We actually did that last time using trig. So if you go back to here, we use trigonometry to figure out the position of the end effector, X, C, and Y, E. So I'm just going to take the same thing. So that will be two of the equations. So I'll write it in shorthand. X equals L1 C1 plus L2 C12 plus L3 C123 equals XREF, right? That's given. And then YE equals L1 S1 plus L2 S12 plus L3 S123 equals YREF. And then the last one is that theta1 plus theta2 plus theta3 equals theta ref. Okay, so three equations, three unknowns. Three equations, three unknowns. Okay, here C1 is cosine theta1, S1 is sine theta1, C12 is cosine theta1 plus theta2. And the same for sine. So C123 is cosine theta1 plus theta2 plus theta3. Okay, so how will you solve it? Well, if it was a trivial equation involving variables for C, well, unknowns were just x, y, x square, not x square, but x, y linear things, and you could solve it. But the problem is it's a non-linear equation because you have cosines and sines. Now it turns out that for some geometries like this one, you can analytically solve for theta1, theta2, and theta3. So I'm going to show you how. So let me take these equations and put them in the new page, and then we'll go from there. Copy. Okay, so first thing we note is that if we know what the sum is, we effectively know that C123 is cosine theta ref. This is known. We know this because theta ref is given. And then we also know that S123 is sine theta ref. That's also given. So what we can do is we have essentially eliminated this equation. This equation has been used. So we can figure out this value is a constant and this value is a constant. Right, so this is here, and then this one is here. So I'm going to rewrite the equations now. I've eliminated one of the unknown, L1 C1 plus L2 C12 equals X ref minus L3 cosine theta ref. Everything in the right side is known. L1 S1 plus L2 S12 equals Y ref minus L3 sine theta ref. Let's just call that, I just don't want to carry this big number, so big variable. So just call that X prime ref, Y prime ref. Okay, so now I'm solving two equations, two unknowns. This is going to be the first equation. So this equals this, and then this part equals this part. Two equations, two unknowns. Okay, again, it's a nonlinear equation because you have the cosines and sines sticking out. So how do you solve this? So this is where you need some ingenuity. If you actually if you square those two equations and you add them up, it turns out that you can eliminate theta 1. So I'm going to square the first one. Equals x prime. Just put x bar here. It's easier later on. X bar f square, and then L1 square S1 square plus L2 square S1 2 square plus 2 L1 L2 S1 S2 equals y bar f. Okay, this summing it up. There's a property of which sines and cosines follow, which is that C1 square plus S1 square is 1. And same thing for 1, 2. So if you add them up, then you get L1 square plus L2 square. So I'm using the fact that C1 square plus S1 square is 1, and C1 2 plus S1 2 square is 1. 2 L1 L2 C1 C1 2 plus S1 S1 2. Okay, now there's one thing about this particular expression. It turns out that there's a trig identity which says that cosine 1 cosine 1 2 plus S1 S1 2 is actually cosine 2 theta 2. Okay, there's an identity which goes that this becomes is actually cosine theta 1 minus theta 1 plus theta 2, or vice versa. It's easier to write it the other way. Theta 1 plus theta 2 minus theta 1, which is cosine of theta 2. Okay, so we've essentially, by doing this, we've solved for theta 2. You need to take the cosine inverse. So I'm just going to write the expression for cosine theta 2. So C2, which is cosine 2, is going to be x bar f square plus y bar f square minus L1 square minus L2 square divided by 2 L1 L2. Okay, and then S2, which is the sign, is plus or minus 1 minus C2 square, where I've used the identity that C2 square plus S2 square equals 1. Now, here's the thing. It turns out that there are two solutions to S2. There's a plus and there's a minus. Okay, so you will see that for the manipulator, you will get two solutions. Now, in general, for the forward kinematics, the good thing is that when you specify the angles, there's only one solution to the forward kinematics. You give the angles, I'll give you the end effective position. There's no, the same angles won't, well, if you give the angles, the forward problem is uniquely determined, but the inverse problem is not. There's a case where you could get one solution. There's a case you get two solutions, three solutions, and there's a case where you got no solutions. No solution, the easiest example is that if you try to find to do the inverse kinematics when the point you define is out of the reachable space, that would have no solutions for sure. Okay, so the key thing is there are two solutions corresponding to the two signs in the expression for S2. Okay, so that's that. But then if you want to find theta 2, what you want to do is you want to use the arctan to S2 C2. Okay, so don't use arc cosine or arc sine because the arc tan 2 is a better way. It gives you the it gives you a value from, it basically takes care of the quadrants too. So use that. So whatever you get for C2 and S2, so if you use the plus, you'll get one value for theta 2. If you use the minus, you get another value. Use this in NumPy. It's actually NP dot this. Okay, so that gives us how to compute theta 2. We still have to compute theta 1 and theta 3. Okay, now that we know what, since we know what theta 2 is from that expression, C2 and S2 are known, right? How do you know them? Well, you know from here, you also know it from here. So once you know C2 and S2, what you can do is you can now rewrite, let me put some numbers to this. Let's call this 1 and 2. So I'm going to rewrite 1 and 2 based on the fact that I know what cosine theta 2 is and what sine theta 2 is. There's a numerical value which I've already computed here. So from 1 and 2, L1 C1 plus, let's go back. So if you see this, I'm just going to expand out L2 C1 2. So the expansion of C1 2 is that C1 C2 minus S1 S2 equals X bar ref. And then there's the second one is like this. So what is known? L1 is known, L2 is known, C2 is known, S2 is known. Again, C2, S2 is known. So I'm going to write two equations now. One equation, in both equations, I will isolate the unknowns, which is going to be S1 and C1. So let's rewrite this. L1 plus L2 C2. So I clubbed all the values, known values together, times C1 minus L2 C2, which is known, times L2 S2 times S1 equals. And then the second one is here L2 S2 S1, sorry, C1 plus L1 plus L2 C2 S1 equals. Okay, now here we are trying to sort of get one of those two. So what you could do is, you notice that there's L2S2 here, L2S2 here. So you could actually, you could treat this as two equations and two linear equations involving C1 and S1. Think of C1 as X, S1 as Y, and then solve for one of them. So you can achieve that by either taking the determinant and doing what they do with cofactors, or you could just work it out this way. You could just multiply. So let's call this 3 and 4. So the easiest way to do this is perhaps, I'm just going to eliminate S1. So how do we eliminate S1? We just multiply L1 plus L2 C2 with 3, and then add it to L2 S2 times 4. Okay, the effect of this is that this term will drop off. So when you do this, you get C1 equals X prime ref x bar ref L1 plus L2 C2 plus y bar ref L2 S2 divided by L1 plus L2 C2 square plus L2 S2 square. So everything on the right is known. We have now found C1. And then you can also find S1 as plus or minus 1 minus C1 square. Here you'll see that one of this solution is extraneous. Extraneous solutions are incorrect solutions. And you'd have to check this manually. Need to check, and I'll show you how to check manually. And the final thing is to compute theta3, which is basically theta ref minus theta1 plus theta2. So we have now computed the solution theta1, theta2, theta3 just by hand. It's a luxury you get for certain problems, not for everything. Let's see if we can actually get the inverse kinematics for the planar manipulator using this. 5 minutes, I think, should be enough to finish this off. I'm just going to write this from scratch, but just use some of the code I wrote down already. Okay, so here my goal is to compute. I'm given x ref, y ref, and theta ref. So I want it to be at 0.50 and with an angle of 90 degrees. So it's vertical. So I have a function which I've created, inverse kinematics, which will compute the analytic solution based on the formulas I derived. And then to verify this, I use forward kinematics to create sol and then animate it. So if you run this, it actually gives you the solution and also makes a plot. So here is the solution. Okay, so vertical. Okay, now let me just show you a little bit about the inverse kinematics. So what I did here was essentially copy pasted the formulas. So I have this x bar ref, y bar ref. I wrote it xp and yp. I computed C2, which is again from the formula. Here, actually, I've just used a random number generator to select one of the two roots. So I said there are two solutions. One is negative, one positive. So randomly choose that. Compute theta2 using the tangent. Then I get C1, which was the last thing I did. I got S1. Now, as I said, this S1, let's just comment this out. What was the shortcut to comment it? Control / It's not working. Okay, there it works. Okay, so I just commented out some parts. So I got S1. I computed theta1. I use arc tangent. And then this. I said there are two solutions to this, S1 positive and negative. So let's just run this and see what we get. See, that's the extraneous root. Okay, so what I did was to fix the extraneous root. This is what I did. I actually run it through the forward kinematics, and I see if the forward kinematics is actually predicting where it should, which forward kinematics basically predicts where it should be. And turns out that it actually tells you that your solution is not valid because it actually went there. So then I take, if the error is large, then I just say I use the other ones. Instead of using the positive one, I use the negative one. And then I proceed with theta1, theta3. And so this ensures that I always get the right value. So if you go back and run this, that's the solution. Now, there are two solutions for this case. You could try a different initial well, here it's actually two solutions are, this is one, I don't know which one of them, but we can quickly check. I'm just going to, so this random number generator, it always generates a number between 0 and 1. So let me just say it's less than 2. So it'll always go through this one. So now if I run this, it gives me the second solution. Okay, so this is the other solution. There are two solutions to the inverse kinematics. The thing is, this particular method actually gave us both solutions. So here, given the random number, it generates one of the two. Okay, I'll stop here.